You think your computer is racing through calculations, doing countless things continuously, in real time, the way a river runs. It isn't. Inside each processing core, it's doing exactly one operation at a time, at a rate that's hard to picture. And for a sliver of every single one of those moments, it isn't doing anything at all. It's frozen, waiting for permission to move. By the end of this video, you'll know what a computer actually is at the lowest possible level. Why binary isn't really a code so much as a physical fact about electricity. Why your CPU is better understood as something that stops over and over rather than something that flows. And the physical law, not a technological limitation, that stops chips from just getting bigger to get faster. Here's misconception number 1, and it's less a factual error than a category mistake. People assume a computer is, in some sense, smart. That processing information requires something like understanding. It doesn't. At the bottom of every computer that has ever existed is a pile of switches, and every one of those switches only ever does one trivially simple thing. It lets current through, or it doesn't. The idea that you could build genuine logic, not just electricity, but actual reasoning, and, or, not, if-then, out of nothing but switches wired together, comes from a single piece of student work. Claude Shannon's master's thesis at MIT, submitted in August 1937, called A Symbolic Analysis of Relay and Switching Circuits. Shannon showed that the true/false algebra a 19th century mathematician named George Boole had invented, a system for treating logical statements like equations, could be physically built using electrical relays, letting a current's presence or absence stand in for true or false. It's been called, without much exaggeration, the most important master's thesis of the 20th century. Every operation your computer performs, no matter how sophisticated the result looks on screen, reduces to some arrangement of that same idea. Switches, combined in patterns, standing in for logic. Here's what that looks like in practice, stripped down as far as it goes. Wire 2 switches so that current can only reach a light bulb if both switches are closed, and you've built what engineers call an AND gate, a piece of hardware that answers the question, is this true and that true, with nothing but wire and metal contacts. Wire the same 2 switches side by side instead, so current gets through if either one is closed, and you've built an OR gate. Add a third kind, an inverter, which simply flips whatever comes in. True becomes false, current becomes no current, and you have the complete toolkit. Every possible logical operation, no matter how complicated, can be built from nothing but and, or, and not, wired in different combinations. Chain enough of them together in the right pattern. Arrange so the switch positions representing one number combine with the switch positions representing another, and you've built an adder, a piece of hardware that can add 2 numbers using nothing but which lights turn on. A few thousand gates can compare values, sort a list, and decide which of 2 instructions to run next. A few billion of them, chained together by engineers standing on the shoulders of the last 70 years of that same idea, can render a video game, decode a video call, or hold a conversation. At no point does anything in that chain need to understand what a number is, or what a conversation is. It just needs to be wired correctly, and it needs the wiring to happen billions of times a second, which is the real answer to where binary comes from. And it clears up misconception number 2, that binary is some kind of secret code, a special language computers speak that's fundamentally different from ordinary information. It isn't a code at all, not in the sense of something invented to be clever. It's a direct description of a physical fact. A transistor, the modern descendant of Shannon's relay, is a tiny electronic switch with 2 stable states, current flowing or current not flowing. Call those 2 states whatever you want. Engineers call them 1 and 0, because that's convenient for math, not because the electricity itself is counting. The 1 isn't stored anywhere as a numeral. It's a voltage sitting above or below a threshold and a wire, and nothing more mysterious than that. Group 8 of those voltage or no voltage wires together, and you get a byte, 256 possible combinations of high and low, more than enough to assign one to every letter, digit, and punctuation mark on a standard keyboard. That's the entire trick behind a computer storing text. Nothing is written down in any pictorial sense. A pattern of switch positions gets agreed in advance to mean the letter A, and a different pattern means the letter B. And a screen full of words is really just an enormous, fast-changing grid of those same two physical states, redrawn from scratch dozens of times a second. The transistor itself has a specific birthday. On December 16, 1947, at Bell Labs in New Jersey, physicists John Bardeen and Walter Brattain built the first working point contact transistor, with William Shockley credited alongside them for the underlying theory. All three shared the 1956 Nobel Prize in Physics for it. What they'd built was a switch with no moving parts, far smaller, faster, and more reliable than the mechanical relays and glass vacuum tubes computers had relied on before. The machine those tubes powered, ENIAC, completed in 1945, used roughly 18,000 of them, and vacuum tubes fail the way incandescent light bulbs do. They burn out. Engineers reportedly spent a meaningful part of every day just hunting down and replacing whichever tube had died since the machine was last checked. A switch with no filament to burn out, no glass to crack, and no moving parts to wear down wasn't just an improvement. It was the difference between a computer you could leave running and one you had to babysit, and a switch that could, in principle, be shrunk almost indefinitely. In 1965, a Fairchild semiconductor engineer named Gordon Moore published a short paper in the trade journal Electronics, noting that the number of components manufacturers could fit on a chip had been roughly doubling every year, and predicting that trend would continue. That observation, later nicknamed Moore's Law, turned out to be less a law of physics and more a self-fulfilling industry target. But it held, decade after decade, closely enough that a single modern chip, like Apple's M2 Ultra, released in 2023, now packs about 134 billion of Shannon switches onto a piece of silicon smaller than a coaster. Quick pause, because the scale of that number is easy to read past without absorbing it. 134 billion individual on or off switches, each one just as dumb as Shannon's original relay, arranged so their combined dumbness adds up to everything your phone or laptop does. Because knowing the switches exist doesn't yet explain the stopping time part. And that's where the third misconception lives, the one about what processing actually feels like from the inside of the machine. Picture 134 billion switches, all wired together, all capable of flipping the instant a signal reaches them. Left alone, that's a disaster. If one part of the chip finishes a calculation microseconds before another part expects it to, the whole system corrupts. A problem engineers call a race condition, information arriving out of order and getting read wrong. The fix, built into essentially every digital chip made since the 1950s, is a clock, a signal generated by a quartz crystal vibrating at a fixed rate that ticks at a perfectly regular interval and tells every single transistor on the chip exactly when it's allowed to change state, and not a moment before. Between ticks, nothing is supposed to move. The entire chip sits frozen, mid-calculation, waiting. Then the clock ticks. Everything that's ready to change changes, all at once, in lockstep, and it freezes again. That's the literal physical version of stopping time. A processor advertised as running at, say, 3.5 GHz isn't running smoothly at some blistering constant pace. It's stopping and starting 3.5 billion times every second. And the smooth performance you experience is an illusion, built the same way a film reel builds motion out of still frames, just at a frame rate roughly 40 million times faster than a movie theater's. Your computer doesn't move through time smoothly. It stops time billions of times a second and stitches the stops together into something that looks like motion. That's worth sitting with for a second, because it reframes something that sounds like marketing copy, 3.5 GHz, into something almost physical. 3.5 billion freezes and releases every second in perfect lockstep across 134 billion switches. If this is the kind of thing you'd want explained about the rest of the device in your pocket, A-like helps this reach more people who'd want that too, and there's plenty more of it still to come. Each one of those individual ticks does real specific work, following a structure that's older than the transistor itself. In 1945, the mathematician John von Neumann circulated a 101-page document called First Draft of a Report on the EDVAC, which laid out for the first time in writing the architecture nearly every general-purpose computer since has copied: a single memory holding both the instructions and the data those instructions operate on, and a control unit that works through them in a repeating loop. Fetch the next instruction from memory, decode what it's asking for, execute it, then fetch the next one. Fetch, decode, execute. Every keystroke, every pixel, every number your computer has ever displayed is that three-step loop, run once per clock tick, an almost unfathomable number of times, back to back to back. Which brings up the fourth misconception, the one about computer code itself, that when a computer processes information, it's reading something resembling the code you'd see scrolling down a screen in a movie. Dense, cryptic, purpose-built. It isn't, not down at the level where the work actually happens. Programmers write in languages built for humans, full of words and structure, specifically so people don't have to think in raw voltage. A separate program, a compiler, translates that human-friendly text down through several layers of abstraction, until it becomes nothing but sequences of those fetch-decode-execute instructions. Plain numbers, telling the fetch-decode-execute loop exactly which switches to flip. Nobody writes binary by hand anymore. Practically speaking, it's not a language for communicating. It's just the last stop before electricity. And that finally gets to the trickiest correction of all. Misconception number 5. If the earlier ones haven't used up your patience, that a computer does many different things simultaneously, the way it certainly feels like it does, with music playing while a document autosaves, while a dozen browser tabs sit open. For most of computing history, that feeling was a carefully engineered illusion, not a literal truth. Before the 1960s, computers ran one program at a time, start to finish, and everyone else in line simply waited their turn, feeding in punch cards, then waiting hours or days for a printed result. In 1961, an MIT researcher named Fernando Corbato demonstrated a fix, the compatible time-sharing system, one of the first setups built to give multiple users and multiple programs the impression of running at once on a single processor. The trick was speed, not simultaneity. The system rapidly switched its full attention between tasks, giving each one a tiny slice of time before moving to the next, fast enough that no human waiting at a terminal could perceive the gaps. Corbato later won the 1990 Turing Award for the work. For decades, multitasking on a single core machine meant exactly this. One thing happening at a time, sliced so thin it looked like several. Underneath the illusion, it was still the same stop, start, stop, start, just handed to a different task each time it started again. Modern chips complicate that picture, in a way worth being precise about, rather than hand-waving past. Most processors today genuinely do contain multiple cores, separate, physically distinct fetch-decode-execute loops on the same chip, each capable of running real independent work in true parallel. Your phone or laptop isn't running one loop and faking the rest. It more likely has somewhere between 4 and 20 of them, each with its own clock, each capable of fetching, decoding, and executing on its own schedule. And even within a single core, a technique called pipelining lets a chip start fetching the next instruction before the current one has finished executing. Overlapping stages the way a factory line has multiple cars in different stages of assembly, moving down the belt at once. One station welding a frame, while the next station over is already bolting doors onto the car ahead of it. So many things at once is closer to true now than it was in Corbato's era. But it's true because engineers built more independent stopwatches, all still ticking on the same underlying principle. Not because any single one of them learned to do two things in the same instant. Each individual core, at each individual clock tick, is still doing one fetch, one decode, one execute, frozen and released, billions of times a second. Your computer doesn't move through time smoothly. It stops time, billions of times a second, and stitches the stops together into something that looks like motion, now just across more independent loops than it used to, all stopping and starting on their own separate beats. So, not smart, just switches, arranged by people who understood logic well enough to build it out of wire. Not a secret code, just voltage above or below a line, grouped 8 at a time into patterns everyone agreed in advance to call letters. Not smooth motion, but a strobe light running faster than anything you could consciously register, freezing and releasing on a beat set by a vibrating crystal. And not one continuous stream of attention, but many small, fast, frozen loops layered together, first by slicing time thin enough to fool a human, later by simply building more loops until the seams disappear entirely. Go back to that opening claim, that your computer is racing through calculations continuously, like a river. It isn't racing. It's doing something closer to what a film projector does, presenting one still, frozen frame after another, so quickly that the gaps become invisible, and the whole thing reads as motion. Except where a movie runs at 24 frames a second, your processor is running at billions, and instead of light through celluloid, the frames of voltage moving through 134 billion switches descended from a single relay in a 1937 master's thesis. Your computer doesn't move through time smoothly. It stops time, billions of times a second, and stitches the stops together into something that looks like motion. And that stitching is so fast and so seamless that it took the entire 20th century, from Boole's logic to Shannon's relays to von Neumann's fetch-decode-execute loop, to build something able to do it at all. The device isn't fooling you on purpose. It's just finished the illusion so thoroughly that the computer is thinking stops sounding like a metaphor. If this changed how you picture the device you're probably watching this on right now, itself somewhere north of 1 billion switches, freezing and releasing in the time it took you to hear this sentence. That's exactly what this channel is for. Subscribe if you want the next one of these. Tell me in the comments which layer of this surprised you the most, whether it was the switches, the clock, or the multitasking illusion. And if you made it this far, like helps this reach the next person who's never really thought about what's happening inside the box in their pocket. One more thing, before you go, that never came up anywhere above. In the late 1960s, the computer scientist and Navy Rear Admiral Grace Hopper started handing out short pieces of wire, cut to exactly 11.8 inches, to anyone who asked her why computers couldn't just be made faster. That length, she'd explain, is roughly how far light, or an electrical signal, can travel in 1 nanosecond, a billionth of a second. It's not a technological limit, it's the actual speed limit of the universe, applied to a circuit board, which means there's a hard ceiling on how large a chip can physically be, before its own far corners can no longer talk to each other fast enough to keep up with the clock ticking billions of times a second at its center. And it's a large part of why, once transistors got as fast as they did, engineers stopped trying to make chips bigger and started instead trying to make everything on them impossibly, unimaginably small. It's also why some of the newest chip designs have quietly given up on the single slab approach altogether, wiring together several smaller chips, called chiplets, sitting closer to each other than one large piece of silicon's corners ever could be, shrinking the distance because nobody's ever going to shrink the speed of light.